So hello everyone, welcome to MatSQ webinar today. My name is Min-Kyu Park and responsible for the Chief Scientific Officer of Virtual Lab. So today I'm here for introduce a new paradigm of materials research, machine learning. So I'm going to say a brief introduction to the machine learning, then CNN is a convolutional neural network and graph neural network. And finally, I'm explaining for the crystallographic convolution neural network. And last of my presentation, I will going to have some tutorials, which include high throughput calculations and bulk modulus predictions by using CGCNN. So I prepared two drawings. Anyone know about these pictures? It's quite famous figures. I think you may feel like I definitely saw anywhere or something weird, right? So the answer is the pictures on the left side is the drawn by the next Rembrandt. And right figure is drawn by Google AI by the machine learning technique. So next, Rembrandt tried to drawing the Rembrandt pictures, and Google AI tried to make a Vincent van Gogh pictures. This is the one successful example about the machine learning techniques. One more thing, I said to my cell phone, okay, Google, then ask, I'm looking for a nice restaurants nearby. And my phone answered that, here it is. And then the results are amazing. My phone shows not only seafood restaurant and Korean restaurant, but also indicate here. I really like to go traveling also. Unfortunately, I only can speak Korean and English. So I ask my phone again, how to say how much is in Japanese. So he answered, "Ikura desu ka?" like this. And also I can ask, how much is it in German? So Google said, wie viel kostet das? Like this. It's amazing, right? How could it possible? This kind of technology, mostly based on machine learning. When and where did the word artificial intelligence begin be used? In the 1950s, the concept of artificial intelligence had mentioned in the Computing Machinery and Intelligence by Alan Turing. And 1956, use of term artificial intelligence in the Dartmouth conference. So what is AI? What do you think the AI stands for? It is quite difficult to explain because this is very complex, but basically it is a technology that enables the machine to understand and learn and reason. This is the concept of artificial intelligence. So what is the purpose of artificial intelligence or machine learning? People wanted to make a thinking machine very first time. Then they thought how to describe neural network by computer. Answer that inspired by human neural network system like this. It's a human's brain. There is a signal here, and this is input signal. And single neuron working like this. Dendrite, cellulose, exon terminals, and they're passing through this single neuron, and then alpha signals going out. It looks like very simple, but it's not easy to describe exactly. We still really don't know about how human brain works. In the neural network I mentioned the previous slide, it describes neurons in the human brain. Input signal from here, right? And output signals here and through the synapse or dendrite and cell body. This machine is firstly a neural network machine. This figure shows the very first neural network, and which is connect input and output node by wire. Each wire is a neural network. It's quite amazing, and Dr. Frank Rosenblatt say it expects will be able to walk, talk, see, write, reproduce itself be conscious of its existence in New York Times 1958. Machine learning have regarded something amazing black box at that time. I prepared a simple and/or problem. For the or problem, only one may be one. And then for and problem, both must be one, right? This kind of things should be one. And or problem is both one thing can be one, will be a plus signal, gonna be out. This is an and or problem. But this simple separable problem can be solved by a single line, right? This area, plus area, and minus area, and also minus area and plus area can be separated by a single linear line. It is well working. However, as always, the simple problem arises. XOR problem. This is a binary classification problem. XOR problem is very simple. When x1 and x2 have same value, result gives 0 or plus. Okay. Look at this table and figures. It can't separate by single line. Again, so OR problem can be separated by one single line and the problem also. But in this case, we cannot solve by single line, right? I cannot separate by or this or like something, but I cannot separate by line. Okay, this is the very famous problem, XOR problem. So Professor Marvin Minsky mentions this simple problem can be solved by multi-layer perceptron. However, no one on Earth have found a visible way to train a multi-layer perceptron good enough to learn such simple function. It means we can solve by a multi-layer perceptron, but it is very difficult to solve because too many variables exist. So it is impossible. This is first AI winters. All right, perceptron is architecture like this. Only the difference is that multi-layer perceptron has hidden layer between the input and output layers. So we could solve XOR problem, which is a binary classification, using a multi-layer perceptron. However, the problem is how to solve this complex each node and each weight values. In 1974, Paul Webers firstly suggested backpropagation in his thesis. After that, Professor Hinton developed this. This concept of backpropagation is quite simple. We know that for the propagation can solve the multi-layer problem, which means can't determine the weight and bias. So backpropagation adopts the partial derivative with the backward directions, output to input layer directions. In other words, the backpropagation is recursively calculated from the output layer to the input layer and proceed. That's why activation functions should be differentiable functions. Okay, this is the forward directions, and this is the backward directions. Calculate value, weight, and bias, and then we estimate the backward direction by using the partial derivative. This is the main concept of backpropagation. So return to the XOR problem. Now we can solve this problem by using backpropagation and gradient descent algorithm. The sigmoid function is most commonly used activation function, looking like this. And this only returns 0 or 1, like a switch. Using this method, we may know which weights or bias affect to the result. These minima are found through the gradient descent algorithm. So I give you one small quiz. Which model is better? Left or right? What do you think? So this model is perfectly separated by a red cross and black cross, right? And this is only like this small one piece of red plus sign is located in here, but it's only separated by a single line. So which is the best? The answer is left one, is good one. Because a right model described only the data it runs well, right? So this is the biggest problem we called overfitting problem. So this is quite overfitting, right? For the this and this model. It cannot solve or something here or something here. So this is the biggest problem in the machine learning. How to overcome the overfitting problem? There are so many ways. So basically, the most ideal way is more training data. But most of the case, it is very difficult to get more data, even experimental or some calculation also. It's very difficult. So many people try the reduced features or regularization method. I recommend the reduced feature and regularization method, but regularization is the most realistic and effective way. There are several ways regularization for data. First is dropout, which is the fully connected node to the partial connected node. And batch normalization. And last one is important, is penalized regressions, which called there are some way, Russell, and Ritchie regression, and elastic rank. I show you two examples. This is a Russell regression, and this is a Ritchie regression. You can see here, and here. Here is loss function in front of the formula, and last term this is actually a simple weight, and the sum of this is the penalty term. So this gives you some data regularizations. So in this chapter, we will learn what is the biggest difference between CNN and ANN. ANN is artificial neural network, or some DNN. DNN is ANN, same meaning, deep neural network or some artificial neural network. So the same meaning. So also, a most important thing, we will learn the network architecture and some terms are related to the CNN, like a pooling or filter or padding or something like that. All right, so it is known that CNN is specialized in the image processing, as you know. It's very famous, right? So look at these beautiful cat and dogs in here. There are two types of image processing by CNN, single object and multiple object detections. So CNN can be used to classification. Look at this here. It's a classification. This is cat. And plus localization, this area located in the cat for the single object detections. And it's multiple for the multiple object case, in the object detection for the multiple objects, like a cat, dog, and dog in here, and cat, dog, and dog. And one of more example is like a Zoom or some WebEx, change it to our background, right? Only except my segmentation, right? So this segmentation method is also by using the CNN method. So this is good example of the CNN. It's an instance segmentation for here, like a Zoom or WebEx. This is one of the representative application of CNN, self-driving car. The front camera automatically detect car like this, and some lane here and here, and some object here, like a small stone or like something like that. So this is the main technology of self-driving car. Another example is this. The CNN can be also applied in the medical healthcare field. Look at this figure, and this is healthy, and this is diseased eyes. So even experts say it is difficult to classify this disease. However, using a convolutional neural network, it is possible to predict with high accuracy whether or not there is a diseased eye. This is very good example also. So the key idea of convolutional neural network is the filter and the weight sharing. You can think of filter as a small window, and inside the window is filled with weight. And this is window, like filter. I mentioned windows, but this is filter. Filter is filled with many kind of some numerical values we call weight, right? So this window going down, left, right, left, all directions, and then going here, there are some weight sharing is occurring. This filter scans the pictures and pass by weight sharing. This is the key idea of CNN. Again, weight sharing and convolving filter is the main key idea of CNN. So the important difference between the artificial neural network or deep neural network and convolution neural network is whether all nodes are connected or not. This is the DNN, it's deep neural network, and this is the CNN. DNN is fully connected, right? This node and this node is all connected together. However, I mentioned previously, CNN have a weight sharing, right? So each of H is much smaller than this case. So weight sharing is performed as a filter pass, which means parameters are reduced. So what is the benefit of parameter reduced? Small parameter, what is benefits? Is also overfitting issues can be solved by a reduced number of parameters I mentioned previously, and they learn local features, right? So local characteristics are well described because it passes by learning the local area. You can also hear this run trained by very small local area, so it can be very beneficial key idea of CNN. So I'm gonna introduce the CNN architecture briefly. I will briefly explain that meaning of convolution, filter, pooling, and fully connected network. So this is the overall schematic diagram of CNN. This is a matter of classifying car, I think. The front part is learning part, this part. There are two parts, feature learning part and classification part. Which part is important? This part is much important than this part because this is just like a DNN or a fully connected network. Yes, it exists here. So all CNN networks can be performed this area. The front part are running parts. The back part is the same like ANN. So picture running part is crucial. I mentioned. This is part constitute a convolution, ReLU, pooling, again, convolution, ReLU, pooling, and convolution, ReLU, pooling, something like this. This is learning parts, repeated. So this is a filter. So I want to explain the image and filter. So this red area is a filter, right? This is the 32 by 32 by 3 images. And this filter is 5 by 5 by 3 filters. These filters pass through the scanning all these images like this or this and this. And each time passed, one number is carried out. Okay. Each part, there are some one number here. So I will show you how the image changed when you apply the image filters. This is original Palace figures. Look at the first. The image is sharpened by apply the sharpen 5 by 5 filter. This is a sharpen filter. This is blur filter. This is edge detection filters. You can see that this is different from this figure and this figure. It's more sharpened, and this is more blur, and this is only black and white is appeared. So this is the how to filter effect to the images. So I would like to explain the stride. It's very important concept in the CNN. So let's assume that there are 7 by 7 image and F by F filter here. The filter scans whole image every single step. This step called stride. How much move every step? Stride means how much move every step, like this direction or this direction, it doesn't matter. So in this case, how many outputs are carried out? This stride, we assume the stride is 1, 2, 3, 4, 5, right? And 1, 2, 3, 4, 5. So 5 by 5 output is carried out. So what if the stride equals 2? Output will be 1, 2, 3, and 1, 2, 3, right? So 3 by 3 output is carried out. Let's generalize. So output size equal to n minus f divided by stride plus 1. For example, image size is 7 and filter size is 3. We assume that. What if the stride is 1? 7 minus 3 divided by 1 plus 1 is equal to 5. Stride 2, 7 minus 3 divided by 2 plus 1 equals 3. But problem is, what if the stride equals 3? Output size will be 2.33. It's impossible, right? It becomes a problem because this is not integer, right? So how could we overcome this problem technically? So we adopt GelPadding. What is GelPadding? GelPadding means inserting padding consists of 0, like this area, make output size integer. So example here, it was a 7 by 7, right? So we apply the GelPadding, it's gonna be 9 by 9, right? And then after GelPadding, 9 minus 3 divided by 3 plus 1 is gonna be integer, right? So we can calculate even this is output is not integer. This is called GelPadding. All right, so when image processing is performed like this, the vector dimension becomes large, right? This is very large dimension, 224 by 64. So therefore, pulling is used to reduce the vector dimensions. In other words, this is compression, right? Assume that there is a vector ending over the convolution. If it is compressed with 2 by 2 filters, it's gonna be compressed to the 112 and 112 by 64. However, data rules cannot avoid. So there are two methods of pulling. First method is MaxPulling. Second method is average pulling. So MaxPulling is very simple, right? You look at this lead area. Which value is max? 20, right? It's gonna be 20. And next is 30 is max value. Sorry, this is MaxPulling, and average pulling is the sum of them and divided by 4. It's gonna be 13, right? So either way, the results doesn't change too much in the by the literature. However, MaxPulling is more popular, I think. Last part, flatten. So flatten is kind of a concatenation. For example, there are 112 by 64, and it's gonna be flattened. It will be just 1D, simple, like this kind of flattened value is carried out. This is very simple, right? Just concatenate all together and then make a one-dimension arrays, and then fully connected network. Okay, so level for the CNN. First, CNN is specialized in the image processing. Second, key idea is weight sharing with the filter and convolving over inputs. Its benefits such as parameter reduction and local feature. We have run lastly CNN architecture and important terms like a convolution, filter, pulling, flatten, and a fully connected network. Next chapter is graphic neural network, GNN. In this chapter, I will tell you how to GNN is used for the basic concept and materials research. CGCNN is the most successful application of GNN. So I introduce CGCNN, and then we are going to tutorial with the CGCNN and some material in the field of the materials science. There are two main conferences in the machine learning, very big conference. One of these MNLFE and one of the CVPL. So recently graph here and here began to appear in the two top keywords, okay? Which means that GNN became increasingly important in the field of the machine learning. Let's see the example. Neural network technology using graph is being applied in the advertisement market or some brain connectivity, and more importantly, recommender system is quite important because we are using Amazon or Netflix. They recommend some which you related of your needs. So this is the kind of the GNN. It's very fit for the recommender system. And graph are often the most efficient way to representing objects, and simple term, point and lines are connected. Graph is not so different, like there are some node and edge and connected. This is just graph neural network. So I'll give you one example today. So the next study is the paper classification study using GNN, right? You can see the cardiac, Doppler, or some T-cell in the sarcoma, lung, something like this. The correlation between keywords connected with the edge is expressed in the graph and is actually classified by follows. This study used a graphical neural network based on the word, and as a result, it showed excellent performance in the classification in the personality of the papers, right? So using this kind of edge and node and connecting, change to the graph, and then they classify which one is related to the paper. This white one is related to the neoplasm, something like this. So it's a good example for this. And most important thing is a social network case. It's very it's very amazing because in this paper, the political perspective was studying using graphical neural network, but the contents or title of the newspaper article was not viewed. Okay, which means it's just people who are interested in something in that study don't care about this. How could it possible that? So they classify only the this guy followed this guy, and this guy followed this guy, and this guy followed this guy. Only this information, using the classification, they know these guys are interested in something, and this guy interested in something, this guy interested in like a political perspective. How could it possible? When we see that, follow each other and use them to define edge and node. This is edge and this is node, right? So we have succeeded in classifying the political perspective using only these informations. It's quite an amazing result, I think. Last example is the recommender system. I really like this. For example, suppose A, this guy, has purchased sports products here, and he has subscribed some specific sports station like this. For example, this he buy this one and he subscribed this one. And if B also subscribed this session, the Amazon or some other seller try to recommend this product to her. Okay, this is a kind of recommender system. This is also based on the GNN technology. Netflix or Spotify is also the same procedure. So I want to explain more deeper, but not enough for today. So let's introduce the CGCNN, crystal graph CNN, which is the most successful application of GNN. So it is the method to predict in the forward direction from the material structure to physical properties. It consists of two things. First part is the structure of the bulk is entered. Like this structure is only entered in here, and then change crystal graph. This is also important part. And second part is the basic properties are output in the CNN layer. So in here or here includes some very basic information are including here. So this consists of CNN graph and encoding. So graphical encoding is convert bulk to graph. Very simple, right? this is the crystal system, and this is the graph, right? In the first step, graphical, we said this procedure we called graphical encoding. Okay, so there are some atom here, and bond here. In case of crystal, it is composed of atoms and bond, right? And you can change the term to the node. Node is atoms here, node here, and H. H is bond, right? Atom is a node. Node H. It's same like this, right? It's quite intuitive. Then assign the picture vector to the node. Various basic information is assigned to the node vector, like here, or here, like element information using one-hot encoding scheme. The H vector is defined as a length of the bond, like this. Yeah, H vector is defined by bond length. It's also very simple. Step 2, the graph is connectivity information. It does not change. This is not change, all right? But only changes this color, right? You can see the yellow to green. We call this value is our picture vector, yellow to green. We call this picture vector value has been changed, but shape is not changed. This is main key concept of CGCNN. So key part is as follows. Orange and green is an atom vector, and blue is a bond vector. So concatenate together like this here. And then using this, we perform the convolution and pulling alternatively. This is just very simple concept of CGCNN. Please Googling for the more details, please. So almost done. So last I show you the performance of CGCNN model here. So in this paper, they compare many important values with DFT and CGCNN. This is the CGCNN and this is the DFT values. So like for like a formation energy and band gap or Fermi energy shear modulus or something like that. But it's very surprisingly is the differentiation, like error is very small, right? Comparing with the DFT. So which means the CGCNN can be comparable to the DFT calculation if you have enough data. All right, this part is the tutorial session. So I'm gonna explain a little bit for the bulk modulus and how to calculate them. So today we are going to perform two things. First one is a high throughput calculation to calculate the bulk modulus. And second part is using the bulk modulus and a structure. We are going to perform, we are going to calculate and training and test for the CGCNN. So first part is high throughput for the bulk modulus. Second part is CGCNN for the predictions. Okay. So bulk modulus is the when isotropic, like a hydrostatic, compressive force is applied to the circumstance. Its value represents to the degree of resistance to not compress. Okay. This is the hydrostatic pressure to the some materials or some substance. It's gonna be a degree of resistance. Okay, so typical value is something like this. Aluminum value, reference value is 64 to 78, but actually depending on the case, so I will show you later. So how to calculate is very important. First, find the equilibrium structures. In Quantum Espresso, perform the structural optimization with the variable cell relax, which means the ionic plus cell relaxation. After finish the equilibrium structure, find the equilibrium structure, make strength structure using optimized structure. For example, we have some optimized structure here, and then we are compressed 30%, -3 to 3% hydrostatic. And then calculate total energy of all things. by using SCF calculation and get volume and total energy for each structures, and then apply the Monacon equation of state to get equilibrium volume and bulk modulus.
On the database menu, search AL. Select MP134 structure. To give strain, go to the Cell tab. Select the Strain menu. Check the Range checkbox. Enter the strain range, -5% to 5%. Interval, 1%. Check the A, B, C, to set as hydrostatic. Click the Apply button. Check the structure list. The all of strain models will be added. Add the high throughput module of Quantum Espresso. Click the Structure Builder thumbnail on the right navigation bar. Change input script. Wave function cutoff energy is 50 Rydberg, and charge density cutoff energy is 300 Rydberg. And set the K-point grid as 20 by 20 by 20. Shift 1 by 1 by 1. Click the Update button. Set the job name and change the ppn to 8. Click the Start Job button. You can check the job status on the dashboard. After finishing all the jobs, refresh the work page. Check the job status is green, which means normally finished. Add the correlation module of Analyzer. Click the Connect button, the plug icon of the right top. Click the high throughput thumbnail. It brings the all results from the high throughput module. Check the results. Copy the volume and energy data. Add the Curve Fitting Tools module of Analyzer. Paste the copied information. Select the type of fitting, Murnahan. Click the Fit button. Check the bulk modulus. Open the right-click setting window on the visualizer. Go to the Tool tab. Select as Download, CIF, to download the structure file. With this structure file and bulk modulus results, you can make a CGCNN training set. Add the CGCNN module of machine learning. Drag and drop the downloaded al1.cif to the CGCNN module. Write the calculated bulk modulus results to the value column. Like this, you can make a training set. At this time, we'll use the first training set. Press the Upload zip file button. Upload the training set, webinar 210225.zip file. Click the CGCNN Model tab, and set the hyperparameters appropriately. Enter the job name and submit the job. Check the job status on the dashboard. After the job finishing, click the Update Status button. Click the CGCNN Results tab. And check the results. Click CGCNN Predict tab, and drag and drop the mp27si.cif file. Select a model from Load Model. Click the Test button. Check the prediction result. Perform prediction to other structures.